thanks for the introduction, Benjamin. I'm quite happy to be able to present to you our work today. Finally, contributing something on my third time here. My name is Jakob, obviously, and this is the joint work with my supervisor from the University of Mannheim. We both are from the chair of AI, so also forgive me if sometimes this isn't really the perfect vocabulary. But the work I'd like to present to you today revolves around calibrating SUMO scenarios, and we like to do so in cases where we do not have an abundance of data. Right, let's start off with the motivation for our work. Sorry, I will try to... our chair is in a cooperation with the city of Mannheim, and my task as a PhD student there is to build a SUMO scenario for them. And this gave rise to the scenario that you see on the right-hand side, which we call Mannheim SUMO Traffic Model, or MaST. And as you can see, we are not modeling the whole city center, but or rather not the whole city, but mainly the city center. And the workflow that brought us there is basically the one that I think is hopefully the recommended one. So we started using the OSM web wizard and then invested a lot of manual work, both by myself and a set of very brave and patient students. To iron out errors that always happen when you import networks. Then we were able to obtain some traffic light plans, which we used. We imported the public transport lines using GTFS files that Jakob mentioned yesterday. Which, by the way, I was quite happy with the topic of yesterday's tutorial, because it sets the stage quite well for our talk, I think. Because really, what we're doing, or what we're trying to do with at least our scenario, is we want to model the traffic that is in Mannheim, and the core question for us is how well are we actually doing this? And the answer to that, unfortunately, at least initially, is quite badly. So what you can see here is, this is the Kurpfalzbrücke. Okay, I can't use a pointer. Which is one of the most important entries into the city of Mannheim. And this is during the morning peak that we're trying to simulate. And as you can see, traffic is bad in Mannheim, but not that bad. So we can see that we get these catastrophic traffic jams. Traffic doesn't flow anywhere. We can't, we can't really get rid of the cars that we're spawning, and then we can't spawn new ones. So this is really a problem. How did we get here? So let me first introduce to you the data sources that we have and what our initial approach was. So we started off by getting data by the city of Mannheim. These were 8 induction loops, so 7 of these deliver bidirectional data, so in both directions. And we can use those to obtain edge counts, and we get those every 60 minutes. In addition, we have traffic cameras, which we can use to get turn counts, so for a given intersection, how many cars go straight, right, or left. And these we have in final resolution, namely 10 minutes. And then we also get GPS traces from commercial provider. We obtained this relatively late during our project. And these basically sum up to 20,000 routes in the end in SUMO. I will talk about why they're relevant later on. As Jakob mentioned yesterday, routeSampler is quite nice for this sort of task, because we can just throw in every kind of data, and it will find a demand distribution that fits this data. And we did this. And the performance was, as I just showed you, a little underwhelming. So, sorry. For the random routes that we tried first, also I have to be transparent here. We didn't tune this very much, so I think this could be improved in theory. But if you just throw in our network into the random trips module, you get 20,000 trips, and we converted these to routes. And when we do this, we get this underwhelming performance where we only simulate approximately 17% of the actual traffic that we have in our city. If we do this for the empirical data that we have, so the GPS traces that we convert to SUMO routes, this actually improves quite a lot. So we are at 40% error rate, which is quite high, I would say, still, but a huge improvement. The problem here, of course, is that routeSampler can't really know what our traffic, what our network really can take. So, as I mentioned, as also was mentioned yesterday, the distributions that are being put out by this do fit the empirical data that we have, but only in theory. And we can't be sure that this is also the case when we simulate traffic, because this is not really what routeSampler is designed to do, I would say. So we present an approach to somewhat fix this, or at least improve this. And the idea is the following. So We start by preprocessing, so both for the empirical data, this means plausibilizing the data from different data sources. We filter the GPS traces, and then we perform map matching. Map matching means we match individual GPS points to edges in SUMO, and then get route distributions. And afterwards, we try to find route probabilities, because as was mentioned yesterday, routeSampler allows for inputting route probabilities together with route distributions. So we have this under-constrained optimization problem, namely we have a set of empirical data that we want to fit, and we want to find a demand distribution that really creates this counts in the simulation. So we try to further restrain this optimization problem by finding a set of route probabilities that lead to this outcome. And I will talk into more detail how we optimize this, but the idea basically is we're lazy, we're using existing SUMO tools and just try to interject some knowledge or optimization from outside in order to get the outcome that we want. And then in the end, when we have our route distribution, we just run routeSampler final time and we get our demand, hopefully. Right, let's start off with the map matching part. Map matching, as I mentioned, is just a task of getting individual trajectories or trips and mapping them to a route network. So in our case, this would be SUMO edges. SUMO has some tools for this. So for instance, TraceMapper, and they work quite well, I would say, in most cases. In our instance, we found that for cases like the one that you see on the right-hand side, this doesn't really work perfect for complex overlaying networks, such as this overpass here. And for this reason, we opted to use a different approach, namely an HMM-based approach. So hidden Markov models are a concept from statistics, I would say, and they can be used to map generative sequences. And in our case, these sequences are SUMO edges. And the trick here is that they allow us to incorporate transition probabilities. So we can then incorporate the connectivity of the underlying graph. And in our case, this really improved the result quite a bit. Right, and then again, we're lazy and use existing SUMO tools. So we use route check and do a router to first flag unconnected routes and then fix them, hopefully, if possible. And in our experience, this really delivered quite a lot more valid routes, and also the quality was better in average at least. Right, now let's move on to the optimization problem and how we tackle this. So let's first define the problem, at least somewhat superficially. So as I mentioned, we're trying to find route probabilities. So we have a set of routes, and for every route, we want to find a probability that we can hover to routeSampler, which will then be used instead of just randomly sampling from the route distribution. So this probability vector is then called x, and it is of dimensions m. M is just the length of the route set. And we want to find the vector that minimizes our evaluation function. And this function is called evaluate demand. And this function takes in the probabilities, x, as well as the route set that we created before using map matching, and the observational data that we have. So this would be induction loops and traffic cameras. We then, for every candidate solution, or for every set of probability vectors that we somehow obtain, we run our simulation, and we compare then the differences between the counts that we see in the simulation and the counts that we observed in reality. Obviously, this only depends on the simulation, so we can't really differentiate this. As I mentioned, I'm from the chair of AI. Normally, we just like to throw deep learning on everything. This doesn't work here because you can't differentiate this, so you can't use backpropagation. So it's a black box optimization problem, and for that, you normally use genetic algorithms. Or often, at least. And this is exactly what we did here. So this is also somewhat similar to work that we've already seen in this conference. In particular, we opted to use CMA-ES, or Covariance Matrix Adaptation Evolution Strategy, which is, I would say, one of the most used approaches in this regard. And it just needs a function that we evaluate, so exactly what we have. The idea is then, for every iteration of this algorithm, we follow evolutionary principles, at least as genetic algorithms use them. And we sample a population of candidate solutions, which we denote as Z. You will note that they again are of dimensions m. And the sampling is guided by a mean vector, so a vector of vector m, that for every probability in our solutions has a mean. So this is our prior, our best guess of what this probability should be. Then we have a covariance matrix, and this is important. So I will not go into detail, but this is important because it allows us to model the interactions between different probabilities. And at every iteration, we then have to evaluate every individual. And we update the parameters, in particular this mean vector. And we do so only using the most successful individuals because we want to increase the likelihood of similar solutions being sampled. You will have noted that I didn't denote the candidate solutions as X directly, so this isn't our probability vector, but rather we want to be, I would say, more efficient still, and want to use more knowledge that we have in our data. And for that reason, we also treat the GPS traces that we initially obtain as empirical data, because I'm sure many of you have already dealt with such data. It's of course not perfect, and the fleets that this data comes from, they only have a small sample of the overall traffic. But still, when there's a route that, for instance, occurs 600 times in there compared to one that only occurs once, this tells us something, right? So it should probably also occur more often in our SUMO simulation. So for this reason, we derive a prior, probabilistically speaking, from this. And this prior is just created by computing the relative frequencies of the different routes in the empirical data set. And then the final probability vector X is given by using the candidate solution to weight these probabilities. And this has many advantages, or two advantages actually. For one, we use the knowledge that we have. And for the other, the algorithm has one scaling parameter. And if the candidate solution would be scaled very differently, which they would have to be, this doesn't really work so well. But if we just use this to scale the prior, this is fine then. We circumvent this problem. Right, and then we just have to do the actual optimization. And we do so in two scenarios. So for one, a 3-hour scenario where we try to model the morning peak. This was the one I started with because my initial thinking was, okay, if I can model the peak, I can model everything, which was a bit optimistic. And then we have a second scenario where we try to model the whole day. We then run 100 generations of 120 candidate solutions. This is due to the number of cores that were available to me on our server. And for this 3-hour scenario, this approximately takes 15 hours on a server. And then, again, to be as efficient as possible, we use the result of this optimization pipeline as an input for the 24-hour scenario. And we run this only for 50 generations, and even this already takes over 6 days. So maybe not the most efficient approach. And this really highlights that we had to do a trade-off between performance and efficiency, because you can see that the curve of the 24-hour scenario probably could have been improved further, but we thought after 6 days, let someone else use the servers as well. Right, for experiments, we then compare different route distributions. So as a very simple cop-out baseline, we have this random routes scenario where we just use the random trips module as it shouldn't be used and just create 20,000 routes which then allow route sampler to match the demand, but it isn't really perfect. Then we have the map matching scenario. So this is just our empirical data that we obtain from the map matching. And we have a weighted scenario, so we can see the effect of using the relative frequencies. Then we have the output of our pipeline for 3 hours. And for the 24-hour scenario, we test two scenarios, or two settings, rather. So for one, just the output of our simulation, of our optimization that I showed to you with a curve. And another one where we allow some rerouting of 20% of vehicles, where we increase the steps per second, per simulated second. And we set the parameter max depart delay to 100. So what this means is that if we can't insert a vehicle into a simulation, after 100 seconds, it's deleted, or discarded, rather. And we follow existing research here. So I think this was from the scenario from one of the scenarios of Ingolstadt. These are our results. So on the y-axis, you see the absolute relative error, RAE. In the brackets, you also see the normalized root mean squared error, which punishes deviations a bit more and is also often used in the literature. And on the x-axis, you see the different route distributions that I just mentioned. And as you can see, for the 3-hour scenario, we improved by quite a bit. So we start off with this underwhelming performance that I mentioned initially, improved by using empirical data, further improved by using the information of how often a route occurs in the empirical data, and then really improve after using our optimization pipeline. And this error is then really in the regions of the measurement error of the data that we have. Because I think this was also mentioned in the tutorial yesterday, routeSampler can't always fulfill the counts 100%, and the error then is in a similar region. So this is really, I would say, quite satisfactory. For the 24-hour scenario, the story is a bit different. So we see higher error rates still. But once we allow this rerouting setting, this really halves again. So again, quite a large improvement. And you also have to keep in mind that the task, of course, is quite a bit harder to simulate the whole day with all peaks and getting the cars out of the city again. And this is the traffic curve over the whole day. Yeah, the colors are not ideal, sorry. The dashed dotted line on top is the empirical counts that we see in the data. The dashed line, which you barely see, are the simulated counts for 3 hours. But you can see that they very closely mirror the empirical data. And then the orange line represents the 24-hour scenario. And here you can see the problem that in the evening peak, we can't really seem to get rid of all cars in a timely fashion. This improves, however, for the rerouting setting. And there we see that we really shadow the curve quite well, I would say. I mean, not perfect, but I would say quite satisfactory, also because our data really isn't perfect. Right, this brings me to my conclusion. So for us, at least, this pipeline of using existing SUMO tools and lazily injecting optimization outputs from the outside yielded an empirically valid scenario. But there are a number of limitations to consider. Crucially, and this is really, I think, potentially the most important point, because what we are really doing here is guessing. So we really have to differentiate between the actual traffic and the traffic that we model, because we deliver one possible configuration that meets the counts, but we can't really be sure that everything that happens in the simulation. So if you, I showed you the image of Mannheim. The inner city is really convoluted, quite a lot of different little streets. And it's very unlikely that we model everything correctly in there, of course, right? So this is really something that we would have to verify by hand, or ideally getting more data. Then again, we are really investing quite a lot of effort to tune for one day. And it would be interesting to see if the probability distributions that we get also generalize to some degree to other day settings and data. Then really crucial as well is the efficiency. I showed to you how long this takes. So we see high iterations counts, especially for the 24-hour scenario. So this is for historical simulation. So the people in the project that I'm in always dream of online simulation. This isn't the way to go for that. And then also we have this route dependence. We have very nice data that cost a bit of money, which we had to spend. So we really rely on these high quality input routes, and you will not always have them. And if you have more empirical data, there are more efficient alternatives, such as just using routeSampler, for instance. I would guess. Right, and for the outlook. So as I mentioned, I would really like to conduct some experiments to see how well this generalizes, or if this generalizes at all. And of course, there are existing tools which work similarly, for instance, Cadis. I hope I'm pronouncing this correctly, I'm always wondering. And another avenue that I would like to pursue is optimizing turn probabilities, because as Jakob mentioned yesterday, routeSampler allows for using those. But I haven't been able to optimize them correctly, because routeSampler samples routes by iterating through all turning count stations. And this doesn't really work very well when the turn probabilities aren't close to reality. And of course, I set out trying to create a multimodal scenario, and I'm only creating cars. So this is still something to do. Right, thanks for your attention. If you have any questions, I happily answer those. If you'd like to have a look at the traffic model, you can follow this link. Unfortunately, we're not allowed to publish the routes that we obtained, which is quite annoying. But still, we invested quite a lot in the network, so if you're interested in this, and this might be useful to you still. And it also contains, of course, all the code that we used for optimization. And of courd, if you'd like to reach out or have any questions, I'm always happy. Thanks.